Hello, good morning, good afternoon, I guess. It's 12:10. Hopefully you are enjoying this. If it's a Friday, it's beautiful weather outside. It's in the 80s. Don't know what the weather's going to be like if this is your Monday effort. But either way, today's topic is going to be reviewing conservation momentum and then starting to dip our toes into the shallow end of our chapter on forces. But make sure that you are ready with a sharpened pencil handy because I'm going to have you guys take some notes today. Make sure you understand some of these ideas. You're going to apply a couple simulations and then you're going to fill out a Google form showing me that you've learned what I expected you to know at this point. So just a quick recap. Okay, hopefully you paused the video and got a pencil and have your notebook ready. We did some videos and we've done some qualitative labs where we smashed some red cards together where you were illustrating the idea of conservation momentum. So let's kind of get a little bit more in the nitty-gritty and let's see if we can actually calculate some of these problems. Let's move me somewhere else so I'm out of the way here. And let's say we've got this situation where I've got a cart with a mass of 1 kilogram, velocity of 2 meters per second collides with a stationary 1 kilogram cart. So this obviously doesn't describe that situation, but that's the image I want you to invoke as we look at this, is that two carts come together and they stick together. What's their final velocity? Well, if momentum is conserved, it means we're going to have the same amount before as after. So in this case, what's going to happen is before the collision, my momentum is P equals mv. And so my momentum of my first cart here is 1 kilogram times 2 meters per second. So 1 kilogram times 2 meters per second means that my momentum before the collision is 2 kilogram meters per second. Okay? This cart right here isn't moving, so it's stationary, so it has no momentum. So the total momentum before the collision is just 2 kilogram meters per second. Now the carts stick together. What's their final velocity going to be? Well, I know that this is still going to be 2 kilogram meters per second because momentum is conserved. That's the whole idea of conservation momentum. But now I've got 1 kilogram plus 1 kilogram, so I've got 2 kilograms of mass. What's the velocity going to be? The velocity has to be 1 meter per second. That's what I'm looking for. If I've got twice the mass, I'm going to have half the velocity. So 1 kilogram moving at 2 meters per second, 2 kilograms moving at 1 meter per second. Okay? My velocity has been cut in half as a result of that. And all to show that momentum is conserved. I've got a 6 kilogram cart. It's rolling at 4 meters per second. So my momentum before the collision is 6 kilograms times 4 meters per second. My initial momentum is 24 kilogram meters per second because momentum is mass times velocity. Here's my mass. Here's my velocity. So my momentum before the collision is going to be 24 kilogram meters per second. So that means that the momentum after is also going to equal 24 kilogram meters per second. That's the law of conservation momentum. So now, if a 2 kilogram block falls on it, now my mass is 8 kilograms. I still know that my total momentum is 24 kilogram meters per second. So what's the new velocity going to be? Well, 8 times what gives me 24? It is now going to travel at 3 meters per second. Before it was traveling at 4 meters per second. A 2 kilogram block was dropped on it. So now its new mass is 8 kilograms. So its velocity is going to slow down in order to maintain that law of conservation of momentum. And you guys did some simulations with that in class Wednesday during your distance learning. You've got a 50 kilogram football player running at 2 meters per second. And they run into a 100 kilogram football player running in the opposite direction. That's key, at 1 meter per second. So if we were to add up our total momentum, P equals mv, we're going to have a 50 kilogram mass times 2 meters per second. But then we have 100 kilogram mass, but it is running in the opposite direction. So we're going to call that a negative 1 meter per second because it's going the opposite direction. So what happens here is that this ends up being 100 kilogram meters per second minus 100 kilogram meters per second. So the momentum is 0 before the collision, which means that after the collision, the momentum will also be 0. What's going to happen? These football players will stop right where they are because they have equal and opposite momenta in this situation. Okay? All of these are trying to show the idea of conservation of momentum. So hopefully you've got that idea down. We've hit it a few times. You're also going to hit it in lab of what momentum is. And hopefully those simulations help as well. But momentum is going to start leading us into forces because in those collisions, objects are applying forces on each other. And the force that we probably experience the most is the force of weight. So make sure you guys are taking notes here because we are going to determine the difference between mass and weight. And a lot of people confuse these ideas, but we're going to make sure that we know the difference after today. So mass is how much matter an object contains. It is going to be the same for an object no matter where you are in the universe. The amount of me is not going to change unless I go on a diet. If I go to Mars, if I go to the moon, if I go to Pluto, if I go to a neutron star, my mass will not change. The amount of atoms that make me up will not change. So my mass, let's say it's 50 kilograms on Earth. If I travel to the moon, my mass will not change. It's still 50 kilograms. The amount of atoms that make me up will not change. Weight, however, is the force on this mass by the acceleration due to gravity. And the acceleration due to gravity is going to be different wherever you go in the solar system. Okay, it's even different in different places on Earth. If I climb Mount Everest, it's less. If I go to the North Pole, it's more. It's slightly different. Okay, so the weight is going to depend upon where you are in the universe. And you're going to measure this with a scale which measures your force against the ground. So let's say if I have 50 kilograms, okay, what I'm going to do is I'm going to multiply that 50 kilograms times the acceleration due to gravity. And we're going to talk about what that is on Earth, which is 9.8 meters per second. So mass times gravity equals my weight. So if I multiply 50 times 9.8, my weight is 490 newtons. Now that's the equivalent of 110 pounds, but we're not going to work in pounds. If I travel to the moon, however, even though it's the same mass, even though it's still 50 kilograms, this person, they look kind of thin to begin with, but they haven't lost or gained weight when they went to the moon. Okay, their weight will be only 1/6 as much on the moon because the acceleration due to gravity on the moon is 1/6 as much. Okay, and what we're going to do here is kind of follow this down the line here. The acceleration due to gravity on Earth, this is a number I'm going to expect that you know, is 9.8 meters per second squared. So we're going to learn about something called Newton's second law of motion. And force is going to equal a mass times an acceleration. So if I know the mass and I accelerate it at 9.8 meters per second squared, that's going to give me a weight. So if that's the case, how much would a 10 kilogram object weigh? I take my mass times the acceleration due to gravity on Earth, which is 9.8 meters per second squared. So the weight of a 10 kilogram object is going to be 98 kilogram meters per second squared, but we're going to come up with another unit for that. We're going to use a capital N, and we're going to call that a Newton. So newtons is kind of like a cousin of pounds. They both kind of measure the same thing, like feet and inches both measure distance. Newtons and pounds measure force, but we are going to use newtons of force because that is the international system that we are going to be working with. This number, all you got to do, mass times the acceleration due to gravity on Earth, this will not change. Well, it will change a little bit, but this is going to be the value we use for Earth. Okay? My mass will not change no matter where I go in the universe. This will change. Okay? This is dependent upon factors we talked about back when we were talking about gravity. Okay? So, I have a couple simulations. I also have a video I'd ask that you try. And then, if you need to review or recopy your notes, I'd recommend that you do that. But then there's a Google form for today that I'd ask that you complete. Okay? Hope you guys have a great day, and we will talk to you later.